It
It's
says
live.
now it's live. Okay.
Now it's
Jesse!
it wasn't live then, but now it's live.
Now it's live.
Woo. That was epic.
Golly.
Hey everybody.
Somebody else is commenting his CosmoQuest. I'm signing out.
Oh, that was that was me. But I don't need to comment anymore. Worst return from summer break ever.
And yet appropriate.
Yeah. But we're back. Hey everybody. Welcome back to the Weekly Space Hangout. I hope you guys all had as good a summer break as we did.
What's a break?
And returned to the Google Plus to find that everything's different, nothing works, it's all different, but we are going to crank our way through a triumphant return of the Weekly Space Hangout.
Yeah, some of us were here all summer. Oh,
All
God, learn
summer,
space, come on.
just constantly publishing.
Yeah.
So if you don't know, I'm Fraser, Cain, publisher of Universe Today, and we've got it is an all-star show, which is great. So I'm just going to run through the crowd. So we've got Dr. Brian Coberline. Can you hear us, Brian?
I can hear you now.
Oh, and you just sound great. Man, this is perfect. This is what being able to hear Brian Coberline sounds like.
Yes.
All right. We got Dr. Matthew Francis. No, can we hear you? We can't. Oh no.
After all of that?
Oh, we may watch Matthew Francis dismantle a computer in front of our eyes.
Rage with the internet again.
Yeah.
Oh, golly.
Or perform interpretive dance of whatever.
Or perform an interpretive dance.
That's already been suggested in the comments, guys.
Is the universe a hologram? Matthew Francis, go.
And is Matthew in it?
All right. Morgan Renberg. Hey, Morgan.
Hey, Fraser.
So much pain.
Dr. Nicole Gallucci.
Stop!
Yay.
Dr. G, as my students call me
Dr.
this
G.
semester, because my name is too long.
Yeah.
Dr. Thad Zabo.
Hello.
Zabo. Wow, Morgan and I are the only ones who
We're the
don't
only
have
non-doctors here.
doctorates. Yeah, and you're working on yours.
Doctor.
Not fast enough.
Doctor. Right.
And then there's Moan.
So today we are going to be talking about whether or not the universe is a hologram. Is the Milky Way part of a big ass supercluster? Spoiler alert: yes. Updates on NASA planetary missions and close-up look at Rosetta. Accurate distance to the Pleiades star clusters or superclusters, which we were talking about, from pebbles to planets. And we're going to talk about what happened at the Parsec Awards this week at DragonCon. I guess we should start there.
I wouldn't know.
Which was congratulations to the Universe Today team for winning a Parsec Award for the best fact behind the fiction. So we've been up for 5 years. Pamela and I have been up for 5 years trying to win with Astronomy Cast. And one time, I'm not sure whose idea this was, they submitted Astronomy 365, and that won. So I've never been able to get my hands on a Parsec Award, and I don't have it at arm's reach, but it's nearby.
Yeah, seriously, how are you not carrying that around all the time?
I have been just setting it. I'm gonna go grab it. I'll be back in 1 second.
All right, you do that. We'll catch up on the comments on the event page. Since there's this new showcase feature, it seems to make the Q&A app look a bit borked for people. However, we have a comment from Simon Love in the Q&A app saying, for those wondering, to access the questions app, click the 9 squares just above the video. I don't know what this looks like because I'm not seeing it. So you can go ahead and do that. Click 9 squares above the video. If you see that, you'll join the Q&A app. Jim Meeker's in there. Simon Love's in there. A whole bunch of you are regular friends, are irregular friends, let's face it. We're all space geeks here. Over in the events page commenting. I noticed we had some suggestions for lyrical Weekly Space Hangout introductions. I don't know if there's anyone who wants to try their singing or maybe their beat poetry voice. Anybody?
I don't do beat poetry.
Okay, well, it's fine. So thank you, everybody. We'll be trying to keep track of the comments on the event page and the Q&A if you can see it. So hooray!
So there you go. There's the Parsec Award. Yay! Parsec Award. So that's for the Guide to Space. The other thing we should give a big shout out to is over the summer, the fans of the Weekly Space Hangout have been a busy, busy bunch, and they've made their own Google Plus community for the Weekly Space Hangout. I think it's called the Weekly Space Hangout Crew, and I'm sure somebody will be glad to link it in the comments over on the event page. It's awesome. There's so many. You guys have been there's like 200 threads, and all of the names that we see there are all in there. It's been crazy. So I heartily encourage this, and I also encourage all of the folks in the Space Hangout to join the community and participate in the conversations, because what we need is another place to have a conversation.
Stop your whining.
I know, it's awesome. So thanks to the folks who did it, and it's awesome.
Keeping it going all summer, and Guido especially for keeping track of all the space-related hangouts that have post.
All right, well, let's get cracking with the story. So I think the big one that broke, I guess, is the universal hologram story, and as always, we want to have a big conversation between Coberline and Francis. So let's get cracking. So Brian Coberline, why don't you introduce this, and then we'll get point counterpoint.
Okay. The basic idea is when they say is the universal hologram, they're actually talking about what's known as the holographic principle, which is a connection between describing things in terms of three-dimensional space and describing things in terms of surfaces. So the basic idea is that if you have a volume of space, you can describe everything within that volume of space by knowing everything about the surface that encloses that volume. It would be kind of like if you are driving down the highway, you want to know if someone's speeding. Measure their starting point, measure their end point, you know what their average speed is. Although in this case, you know everything that's in the volume. So it's an important mathematical idea in approaches to quantum gravity. So string theory, loop quantum gravity both rely upon these types of ideas. So there's a new experiment that's being set up at Fermilab called the holometer, and it is trying to find these small chaotic fluctuations within space itself that they argue would be indicative of this holographic principle applying. So that's where the news comes from.
And I'm assuming that folks at everywhere went crazy and said we all live in a big hologram and what this means.
Right.
So, Matthew, how did you digest that response, and how do you respond?
Well, first, let's see if my mic... Can you actually hear me now?
Yeah.
Yes.
All right, great, finally. Things were working for 5 minutes at once. That's pretty good. Or holometer, I don't know which syllable the accent is supposed to be on, is that it's testing one particular theory that is, shall we say, not very well regarded among the people who study this stuff. It's testing something known as holographic noise, which is, I'm not even sure what status that has in the community of people who study the holographic principle. But it's basically the idea that on the very smallest scales, the Planck scale, which is the smallest length that is easily defined, supposedly the scale at which quantum gravity works, there's going to be some kind of pixelization, as they put it. And the notion is that if you can build two very precise interferometers, basically two devices that are built of lasers in an L shape, they bounce the lasers in two different directions, send mirrors at the other end, send them back, recombine the beams, and then figure out whether there's fluctuations in the length of the paths that these laser beams are traveling. You can see if there's this holographic noise. So basically, if the holometer works as advertised, it may or may not be able to detect this holographic noise. If it doesn't detect the holographic noise, it doesn't tell us anything about whether the universe is a hologram or not. And the other part of it is that you need to be really, really sure you understand the noise in the holometer. And this is something that, this experiment may actually sound familiar to a lot of you. It sounds very similar to LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO has basically spent 10 years trying to understand the noise in the system. It's not easy. The advanced LIGO, which is coming online very soon, they've really done excellent work in figuring out what the noise is. So I don't know if holometer is anywhere close to that. So I am pessimistic about it, which I know shocks everyone in this group. But don't bet money on whether this is going to say anything about whether the universe is a hologram or not. So, so this is not actually testing if the universe is a hologram. It's testing if there's holographic noise, which is not the same thing.
Right.
So that's the short version of a short summary of the long-winded explanation.
That was great.
If we're talking about noise on the Planck length scale, the chance of fluctuations from that getting up to any kind of energy or length scale that we're actually capable of detecting at this point, this is a reach. This is a real reach.
They're able to detect things on the attometer, whatever that is, 10 to the minus whatever. What is attometer?
Let's see. So
10 to the
15, minus 18.
10 to the 18th. Yeah.
Yeah. Which is pretty small, but it's still not the Planck scale. You're right.
Right.
So, but the idea is that the noise should exist on fluctuations even above the Planck scale. And again, we can discuss that in more detail, but it's, yeah, again, you really have to understand the noise very well, and I'm not sure that, not sure they have done so.
My understanding is that this is really more of a proof of concept, despite the hype.
Maybe.
I mean, just in the sense of it's set up to see if they can even do this. Something like the first LIGO experiments, which the whole point was just simply to see if it can even do anything. But it's not very highly regarded in terms of that particular version.
Yeah, except we know gravitational waves exist, and we don't know if holographic noise exists.
Exactly.
How big is this thing? LIGO is huge. Is this room-sized or building-sized?
It's 40-meter arm length.
Yeah, it's lab size, so 40 meter.
Sorry.
But it's a
Okay, well, you know what?
It's another Fabry-Perot recycling. They bounce it back and forth, so it's effectively longer than 40 meters.
Right.
We could speculate about this all day, and,
we got less
the sort of deep and disturbing, implications of us possibly living in a hologram. But why don't we move on, because I know Dr. Zabel's got a book pretty quickly here. So, and you were going to talk about the new supercluster that we find ourselves in.
Right. I mean, mainly because my research is on galaxy clusters. And if you ever read a paper on galaxy clusters or go to a conference where they talk about them, the first sentence is galaxy clusters are the largest gravitationally bound structures in the universe. So we get this idea of superclustering coming along, and it's like, wait, this looks like something bigger. And it is, except the universe is expanding. And with the understanding of dark energy, with the expansion that's going on, at some point in the past, yes, these objects were gravitationally bound, and that did impose a flow. So we see this great attractor in our region of the universe, and if you put together the peculiar velocities, meaning the velocities if you subtract out the Hubble expansion, things are being drawn into this large, massive area near the Centaurus cluster. However, you can't just throw that out, and so in reality, we are getting farther away from the great attractor. But what it shows is it gives an idea of universe earlier on where dark energy hadn't taken over like it has at this point, and these objects were gravitationally connected, and it imposed this overall flow in the local out to 500 million light years universe.
And so now we've got a name for this supercluster, which you have been avoiding.
Laniakea?
That sounds pretty good.
Okay.
Laniakea?
Right. So what the measureless, measureless heavens, right? They're beyond measure, and from Hawaiian, because there's so much of the research here. If you're looking at information from Keck, from Subaru, etc., right? That's coming from scopes in Hawaii. So let's honor Hawaiian traditions and Hawaiian deities and whatnot, and ideas with the name here.
Question,
And
Dad?
Yeah.
Have you got a picture? I don't know if people have noticing. I've been trying to put up links to the stories using this new gadget, the Showcase app for Google Hangouts, and I don't know whether people are seeing this.
We have figured out how to get them to switch back and forth between Showcase and Q&A. So I already posted a screenshot showing you how to do that in the comments on the event page.
Yeah.
So thanks to Simon Love for pointing out that. So they can see the Showcase.
So they are able to see the Showcase. Okay, great.
They open the Q&A app, which is also the Showcase app.
Okay, great.
The other thing-
the Showcase app is the Q&A app. Okay.
Yeah, they can
We
switch.
can also post some pictures. I don't know if anyone's got a picture here.
Even better than a picture, though, the group that did this has their site on cosmography, and I posted an article about it or just a quick write-up on it on Google+, and it shows 3D views of the supercluster. So you kind of zoom in and zoom out and rotate 90 degrees and rotate 90 degrees, and it really gives you a feel for what the overall structure is. You can see that we're on the edge of this void, and you can see, okay, well, here's this kind of plane of galaxies and filaments that cut across. The video is about 17 minutes long. I think it's worth the watch. I mean,
There's
you really get a sense.
shorter one too
of-
on the NRAO newsletter page.
Okay.
Not
I didn't
newsletter,
put in that
sorry,
one. I found the 17-minute one. I'm just like, wow, this is just incredible to get a look at this from this many angles, and that we have data that's this good and in 3D.
They have one that's 1 minute and 40 seconds on that I can share.
Well, we're not putting it up because then we'll get a takedown request.
You know what I mean?
YouTube.
Share the link.
Yeah, yeah. Now, can everyone in the Hangout be able to share links into the, or is it just me?
Let's find out. I think it's just you. I don't see how to do it.
Okay. Well, I put up it looks like a squid or like a jellyfish.
Thad, I have a question. This
Sure.
story's come under some criticism. Some people are saying, oh boy, they rediscovered the Great Attractor and gave it a different name. How is this different from what we've already known about our local supercluster and the Great Attractor?
One is the scope and the precision at this point. I mean, really, yeah, it is kind of just an extension of that. But the size of the extension and the precision of the data involved is worth talking about.
Okay.
That before this idea of massive amounts of data. If you look at the Sloan Digital Sky Survey, right, we have data on close to more than 100 million galaxies, right? Some idea of how far away they are in space, and we have redshift data for 2 million of them. And a lot of that is even beyond what the supercluster is. And that's kind of, when I'm about to meet with my students, and the idea is, well, our catalog starts outside the supercluster. Mm-hmm. But yeah, so if we're talking literally hundreds of thousands of galaxies worth of data. And so it's, getting precise measurements on the redshift and comparing it with the Hubble flow. And having some independent measure of distance, because typically you would use the redshift to get the distance. Well, that won't work in this case because you can't get what the velocity is relative to each other or relative to the Hubble flow if you do that. It's like, okay, well, I got this redshift, so it must be at this distance. You need an independent measurement of distance for this to work, and to be able to do it with this large a data set is unprecedented.
Cool.
Now, does this, you brought into this that it tells us a bit about, like, now that we're including dark energy, the expansion of the universe, things like this. So, what kind of structures do you think we would see if we just kept going bigger and bigger?
So here's the issue, right? Anything that's in a galaxy cluster will collapse into that galaxy cluster. So what you will see is essentially fragmentation of the supercluster. The filaments will still exist between them, but even the Virgo cluster, there's redshift between the Milky Way galaxy and the Virgo cluster. So if you could freeze the Hubble flow, which you cannot do, right, we would be moving toward the Virgo cluster. But because the space between us and the Virgo cluster is expanding, it's like, well, you're at this point in space, you're at this point in space, and now there's more space. And so even though gravity would be drawing us in, that expansion of the universe is carrying us away. So you'll see kind of this fragmentation, the filaments will get thinner, and then you'll have just galaxy clusters off on their own. Hey, I can't talk to you or get to you anymore. I can't get to you either. And there they go. Right? But not just this, it's all of them in every direction getting farther away from each other.
Very cool. All right, well, let's move on.
And I got to go.
You got a book, right, Dad?
Yep.
Oh,
right.
It's absolutely pleasure. Great to see you again.
Good office hours.
Where can people find out more?
So you can follow me on Twitter @AstroThad. You can find me on Google+, and hopefully now that my class load this semester is not 8 obligations, I'll be able to do more of that.
Okay, great.
All right.
Let's see what it's at.
Take care.
All right. Let's keep rolling. So, Morgan, let's have a conversation about Rosetta.
Yeah, so while we were on break,
That happened.
Finally did something. So it's been traveling now for about 10.5 years. It launched in early 2004. So an ESA mission, and they're heading off, or they were heading off. They are now at a comet, which I will attempt desperately to pronounce here as Churyumov-Gerasimenko.
Churyumov-Gerasimenko.
Churyumov from here on out.
Churyumov. We can also just call it 67.
It's Emily Lakdawalla. That's her name for it, and we're just going to roll with it.
Wow. I wouldn't want to dispute Emily. And so after 10.5 years of flight, they basically finally caught up to this comet. And unlike a planet or even a moon, this comet has so little mass that they couldn't just fly out to it and use the gravity of the moon or of the comet to sort of catch it into orbit. They had to do kind of like planes intercepting one another and find just the right angle to approach it so that their relative velocities are very small. And so they're traveling around the sun, somewhere between Mars and Jupiter right now, at about 55 kilometers every second. And yet, at the end of this 10.5 years of maneuvers, their relative velocity is only about 1 meter per second. And right now, they're about 100 kilometers away, just kind of hanging out there, looking at the comet. And here I have a video of the approach here. So here is it approaching the last few 100,000 kilometers up to this comet. And over the next month or two, they're going to sort of slowly edge in from 100 kilometers to just a few meters away, at which point they're going to drop a lander onto the surface of this comet named Philae. And the comet has so little gravity, in fact, and then we can see it. Just a still close-up picture here. It looks like a duck. This comet has so little mass.
I've got a still up, Morgan. You can keep going.
Okay, yeah, this comet has so little mass that the lander isn't going to be able to just fall down onto the surface. They're actually going to have to shoot a harpoon into the surface and kind of reel themselves in. And then once they're there, they're going to be able to make measurements of the surface of the comet for the very first time. And so we sort of understand, we know what most of the planets are made of, what most of the moons are made of. We have a good idea of what the surface of some asteroids might be made of based on meteorites, but we don't have a lot of information about the surface of a comet. And this is really our first opportunity to get that. And that will start happening in November. Fingers crossed.
Isn't it amazing how much this thing just looks like an asteroid? I mean, when you look at that picture, now that we're up close, it looks really similar to any asteroid. And I know that in the last couple of years, astronomers are really starting to have less and less distinction between what is a comet and what is an asteroid. There's very rocky, icy asteroids and very, icy or very rocky comets, and that there's just this lack of, or this real blend between what's one thing and what's another thing. And if you take any asteroid, move it close enough to the sun, it's going to behave like a comet. You take and so it's amazing just to see this, because like it's just dark gray. It looks like it looks like a collection of rock as opposed to a beautiful pristine ball of snow and ice that we would expect that Armageddon taught us it should look like.
That wasn't even a comet.
Yeah, that's the kind of big takeaway from Rosetta so far, is it's much darker, much dirtier than expected. Sort of the classical description of a comet is as a dirty snowball. But now, as you sort of allude to, we're sort of beginning to think of comets more as snowy rock balls than the other way around, and they're really just kind of look like asteroids with some more snow and ice on top of them. And we got a sense of that from Deep Impact about 10 years ago now, and we're going to get a much better situation by actually basically going there and scooping up some of the surface and being able to do a full analysis of it in the coming year.
So when's it all gonna happen? We're waiting so patiently.
Yeah,
When is it gonna harpoon the poor comet?
Right, so next week they're going to announce the final landing site. They have it down to like 3, I think, right now. And they're selecting between several different possible landing sites, and that'll happen next week. And then between then and sort of mid-October, they're going to kind of inch their way closer to the comet, because right now they're about 100 kilometers away. They're going to move to 50 kilometers away and kind of reevaluate things. And then they're going to move in, because they have to be just meters, hovering just meters above the surface, in order to drop this lander. And that'll take about a month or so to do. And then I think they're targeting November 11th right now as the day for Philae, the small lander, to hit the surface. And then I imagine there'll be a couple of weeks of checkout and things before they start making observations. But after 10.5 years, we're right there. It's really on the edge now of beginning to do this science.
Well, I mean, if people can feel free to look through our archives, but we were super, super, super excited about this mission and it arriving at Rosetta, and the reality has gone way beyond my wildest imagination. And I was excited that this was even going to happen, and just now that we're seeing even just the structure, the fact that it looks like a rubber ducky, as opposed to a ball, is really surprising. That it had such a strange and elaborate shape.
Right, so this is bringing questions up. Is this 2 comets that at one point in the past merged together? Or is this one comet that formed very inhomogeneously, and as it passes by the sun every few years, it's been eroding and evaporating in a non-uniform way? And so it was once a sphere, and it's kind of eroding away, kind of like some of those strange rock formations that you see out west.
Or did it spin up and sort of get that oblong shape, and then maybe
when
since?
They were coming into it, there was some initial concern it might be a contact binary, which is where you have 2 objects that aren't actually connected, they're just touching, and their gravity holds them together. And that would have been a challenge to try to land on. But it seems now that it is one solid object, just very strangely shaped.
Yeah, phenomenal. This is the best. And now this just gets me more excited for what's going to happen next year with New Horizons. 2015, we're going to come past Pluto for the first time. And as I mentioned, I always mention this, that we will now be able to put aside all of the classic pictures of Pluto that we've been using for 15 years, and we'll have some new pictures to show. I can't wait.
Oh, there's one other big comet activity that's going to happen before New Horizons gets there, and that's just coming up in a couple of months. Right as MAVEN arrives at Mars, comet sighting Spring is going to make one of the closest approaches of a comet to a planet in centuries. It's going to pass within 100,000 kilometers of Mars. Its coma, the tail of the comet, may actually envelop the planet, and MAVEN's going to be right there with a front row seat to observe a comet more closely, an active comet more closely than anything before. And that's a different kind of comet than what Rosetta's at. So Rosetta's at sort of an inner solar system comet. It hangs out inside the orbit of Jupiter, basically. Sighting Spring has come all the way from the Oort cloud. It's what we call a dynamically new comet, and it's been traveling for millions of years. This is the very first time in billions of years that it's getting close to the sun. And so what we're going to get a chance to look at is some of the oldest, most preserved material from the early times of the solar system.
That's just going to be crazy. I wonder if they could retask it or move it so it could get a little closer for an approach, like put it to a higher apogee. What do you call an apogee around Mars? An apoapsis? I don't know. Anyway, a higher apogee so that it could. Man, I've been playing too much Kerbal Space Program. So it gets closer to the comet as it goes by. So we get closer than 100,000 kilometers.
Yeah, I mean, you can only do a small percentage of 100,000. They're thinking about maybe trying to turn around the Mars Reconnaissance Orbiter, which has the best camera of any spacecraft mission ever. And supposedly, if Curiosity looks up from the surface when Sighting Spring makes the closest approach, it's going to stretch across the sky, like we've all seen in Game of Thrones.
Yeah.
That's great. Okay, well, let's move on. Next up, Nicole. Do you want to talk about pebbles turning into planets?
Yes, we're talking from pebbles to planets. This is a story that was reported by a press release from the National Radio Astronomy Observatory with a gorgeous picture to go with it. I don't know if you have that, but I can screen share. If not, using the green.
I'll make it happen.
What? Okay, you'll make it
happen.
happen. You have the link. Okay. So the Green Bank Telescope was used to look at a portion of the Orion Nebula. Orion Nebula is a very familiar object to those of us who go out and look at the night sky, especially with the small telescope. We know it's a very active star-forming region. And in one particular part called the Orion Molecular Cloud Complex, they took images of these filaments of dust in this region, kind of above we normally look at the Orion Nebula. And they used an instrument with the acronym Mustang. I have no idea what it stands for, but it has a really cool acronym. And that means that they're working at the highest frequencies, or the shortest wavelengths that the Green Bank Telescope can look at with that instrument. And by looking at, oh, there we go. So the purple is the optical light that we're used to seeing for the Orion Nebula. The orange is the radio map that was added with the Green Bank Telescope using Mustang. And by looking at the spectra of these orangey filaments, of course, not really orange, it's radio, these orangey filaments, they were able to determine the size of the sizes of the things in there that they thought were dust grains. Usually we see planetesimals, which are like, asteroid-sized, or we see dust grains, which are like millimeter-sized. These were more like centimeter-sized, so like the size of my finger, right? So they're actually able to detect this like stream of gravel or pebbles that is warm and thus giving off this microwave emission. This is kind of a new size scale that they haven't seen before that is either forming, going into systems and forming new systems, or it may have actually been expelled out of forming planetary systems, leaving this like this streamer of gravel. In fact, Jay Lockman calls it a long and winding road in space behind it.
That's awesome. Yeah, we had that picture on Universe Today, I guess a couple of days ago as well.
Yeah.
Now I know with radio observatories, I mean, it's so hard to build up those maps. I mean, they've really got to just they build them up like what, 1 pixel at a time. So are we just seeing like one little portion of it? And if they just spent more time and just mapped out the whole area in more detail, would we see this in all directions, or just in just this little area?
That is typically the case. However, Mustang is not just 1 pixel. It's a bolometer. It's in that fuzzy region between like traditional radio receivers and you're starting to get into infrared. So being a bolometer, it's actually a camera. It's got pixels on it. There are multiple detectors on it. So they didn't have to build that one up pixel by pixel. But I think they did have to map over piece by piece that region.
And so if the pieces in the nebula are, I guess they're bigger, the pebbles are bigger, I mean, are we seeing these form, I'm sure, sort of compose this? So, like the traditional idea is that you get these little grains and they're all come together and then you get the star and the planets around it, right? And then you get these pebbles starting to form in the protostellar disk, and then that clumps up and you get the asteroids and eventually planets, and then they smash into each other and it's a good time. So you're getting these accreting into larger objects earlier, before they're coming together as these protoplanetary systems. Is that kind of what we're getting at?
I think that's kind of what we're either that they're... Go ahead.
Yeah, I can put this in a little context.
Sure.
So we have this big problem in planet forming theory right now, which is we know how to get from the early disk of gas and dust that makes the star, and then you have a bunch of gas and dust surrounding that new star. And we can get that up to the size of like grapefruits. And we know what to do if we have boulders the size of, say, an SUV. We can build those guys up all the way to the size of planets like Mars or the Earth. But getting from the grapefruits to the car is a really big problem, because they start to get big enough that they start to feel drag, basically atmospheric drag, and this steals all their energy and they fall into the star. And it seems from our simulations that you never get these car-sized objects. And the latest theory that's sort of been put out here is that rather than going right up to these grapefruit-sized objects that then start spiraling into the star and going away forever, we get stuck at this pebble stage for a while. And then those pebbles kind of get close enough that they can immediately collapse down into these car-sized objects. And you can pretty much bypass this grapefruit baseball kind of size regime that causes so much problems. And so to see actual observational evidence of these pebbles is really important, because from now up till now we've basically just been hypothesizing with computer simulations that this is what might happen.
And so maybe I guess if they do form in the solar system, they do all get wiped out, but it's because enough of the car-sized objects and above have been able to find each other that you'll even have planets at all.
Right. The mass of the original disk is many, many, many times larger than the mass of the planets left over, 10 or more times more massive than all the planets and comets and asteroids, etc. left over. And so it doesn't have to be a particularly efficient process to work, but the old way was like 100% inefficient, and you basically just left with nothing.
And so could you end up with maybe like much larger objects, like even planet-sized objects having come together in these nebulae, and then those being part, I guess, eventually being part of the process as they start to come together, and you get the protoplanetary disk forming, right?
Yeah. So there's different ideas about how you can form planets, and if you can form a big planet like a Jupiter kind of planet while you still have a big disk, then the gravity of that planet can do all sorts of things in the disk and kind of stir it up to form more planets. And that's one possible way to form a bunch of smaller planets from one big planet. But again, these are very difficult observations to make, and so we're mostly left conjecturing with a bunch of computer simulations that are always pretty imperfect.
Well, conjecturing is our favorite thing to do. So.
Well, and it's good that now, like you said, they have the evidence, the observational evidence to back that up with Mustang.
Evidence.
Cool.
Awesome. Okay, so let's go back to Brian, and we're going to talk about it. And finally, an accurate distance to Pleiades.
Finally, an accurate distance to Pleiades. The background Finally again. Yeah. The background of this is that for things that are not too exceedingly far, one of the ways you can do to measure stellar distances is something called parallax. And basically, you can look at where a star is relative to something distant, and then as the Earth goes around in its orbit, you get another point of view, and you can find out where that star appears relative to something distant. It's the same type of thing as if you hold your thumb up and look at it with one eye and then look with the other, and you can see that shift. That works really well for individual stars that have a clear sight to the background distant stars. It doesn't work as well for clusters because you've got dust, you've got other stars. It can be hard to see what's in the background. And there's ways to mitigate that, but you can have a challenge. So the Hipparchus satellite that's supposed to be measuring the distances to all these different stars, measured the distance to the Pleiades and got a distance of about 350 light years. When compared to things like the Hubble and other ground-based ones, it was bigger than 400 light years. So you had this disagreement between Hipparchus, which was supposed to be really, really accurate, and some ground-based observations that were putting it farther away. So there's been a recent measurement done by the VLBI, the Very Long Baseline Interferometer, which is a collection of radio telescopes where you can get a really precise parallax measurement. And what they found was a distance to the Pleiades of 440.0 light years. So they got it to 4 significant figures, not 3, which is in complete disagreement with Hipparchus. And this result is solid enough that Hipparchus is definitely wrong. It is absolutely and definitely wrong. So we now know the Pleiades is 440 light years away from us. Where this gets interesting is Hipparchus is supposed to be an accurate measurement of stars and star clusters. Gaia, which is still coming up online, uses similar algorithms. And so its distances may come into question. So part of the thing that this result does is it makes us reanalyze both the Hipparchus data and the oncoming Gaia data based on what we now know.
So this changes everything.
It changes cluster distances, which we've known has been a problem for a while, but now we absolutely know that it's not just a minor problem, it's a major problem.
Yeah, getting distance to things in space is hard. And if the parallax is like the beginning of the whole ladder that astronomers use for distance, right? And so if it turns out, and the places to look for any kind of star you want is a cluster. You know, you want to find a mirror variable, look in a cluster. Want to find a blue straggler, look in a cluster. And so that's like your go-to. That's your shopping mall.
That's exactly it. That's where the challenge comes in.
Yeah. And so now if you can't trust that method of finding out the distance to stars, so could they, modify Gaia's methodologies, or are they just going to have to look in the data in different ways?
They should be able to modify Gaia's data. I mean, the raw data is the raw data, so it's how it's processed with the clusters. And so, as far as I know, no one's doubting the actual instrumental data of Hipparchus. They're doubting what the algorithms are in terms of calculating the distances.
Right, because Hipparchus parallax as well, right?
It is.
Right.
It is parallax.
The VLBA method is parallax, which is the basic geometric way of figuring out distance. And so is Hipparchus, so is Gaia.
Right. But the Hipparchus is in the optical.
Right.
And so it doesn't use the same. Radios can do alignment in and of themselves, whereas with visual, you can't. I mean, it's a slightly different technique method. I'm not the expert in radio, so you have to talk to Nicole.
I know how the VLBA does it, but I just wanted to make sure I knew I was correct in thinking that Hipparchus also was using that.
Yes, they're both using parallax.
The way they calibrate it.
Right, it's all the calibration because of radio versus visible, and so that's where the question comes in. Is in the calibration of things.
Radio wins.
Radio wins in this case, that's for sure.
I love the VLBA. I'm sorry. The first
okay, so
telescope
Morgan,
I
need you to channel your best Casey Dreyer.
All right.
And tell us some news about NASA.
Yeah. So over the summer, NASA convened a panel, which happens regularly, called the Senior Review Board. The Senior Review Board has the job of reviewing requests for mission extensions for all sort of legacy spacecraft missions. So if we take a step back, when you propose a mission to NASA, you say, hey, NASA, I want to build a mission to Mars, since that's where they mostly go. You are given a budget by NASA, basically. You compete, you win. NASA gives you a budget, say $600 million. In that, you have to build your spacecraft, you have to pay all your people, and you have to tell them how long your spacecraft mission is going to last. Because every year that it lasts, you have to pay more money to support people and engineers and all of that stuff. And so you set a finite lifetime for your mission. And in the inner solar system, they tend to be pretty short. Opportunity and Spirit, for example, were 3 months. So was Laddie, observing dust at the moon. Maven, which is on its way to Mars right now, is a year. In the outer solar system, they're a little bit longer. Cassini's initial mission was 4 years. Of course, this takes place after you arrive at your destination. And that's done basically for budgeting purposes. Once your lifetime is up, you basically have to go back to NASA hat in hand and say, we'd like to keep going. And they'll either say yes or no. And if they say yes, they give you the money basically to continue your mission. And it's not a trivial amount of money. A small mission like Maven or Messenger or Opportunity costs about $20 million a year to operate. A big mission, and right now we have two of those, Cassini and Curiosity, they cost about $60 million a year to operate. Of course, NASA's budget has been pretty stagnant over the last few years, and so they're feeling the squeeze on these missions. And so each mission has to justify why they should be extended. You have to prove that your spacecraft is healthy and is likely to remain healthy for the duration of however long you want your extension to be. And you have to prove that you're going to do new science. You can't just keep making the same measurements you've been making and say, we're just going to keep racking up the data. You have to propose new things to do, new investigations to undertake. And so this year there were 7 missions applying for extensions. And back in May, they all went in front of a pair of panels and did this justification. And then in July, the panels basically came up with their answer, gave it back to NASA. And just a few days ago, we were finally, that information was made public. And all 7 missions received extensions, but they all didn't receive equal comments from the review panel. Because the panel, in addition to having the power to say, yes, you should or should not fund this mission, they can recommend that NASA make changes to the mission. Say, well, we should fund these parts, but not these parts. And so the best mission of the 7 was Cassini. Cassini received a unanimous excellent score. They've been now around Saturn for 10 years, and they're proposing to do a final 3-year mission. After 3 years, Cassini's going to be out of fuel. And so that's looking like it's going to go forward as planned. They have a whole slate of new science to do that they haven't had a chance to do in the first 10 years. Then there were some surprise missions like Opportunity. A lot of people thought Opportunity might get canceled because it's also been there for 10 years now. It was only supposed to last for 3 months. And now with Curiosity on the surface, it's kind of looked like a soft target for a cut. But the panel was very, very positive about what they had to say about Opportunity's mission plan going forward. You can't say the same thing about Curiosity. I've read a decent number of these NASA reports in the past, and I have never seen a more bald-faced negative review than I saw of what was said of Curiosity. Excuse me. The first thing they said is Curiosity drives too much and does science too little. And so, you know, for the last year or so, they've basically been driving towards this mountain, and they only stop once in a while to look at a rock. And the panel basically said, stop more, look at more rocks, drive less. You're there not to set distance records, but to actually do science. Then they called out directly the project scientist of Curiosity for not even showing up to these defense meetings, basically. And they ended with the comment saying that the Curiosity team felt that they were too big to fail. And recommending that NASA refocus the team before giving them additional funds. And that's about as harsh as bureaucratic language as you're ever going to hear come out of NASA. But, you know, in the end, it turns out they are too big to fail. They approved the extension anyway, because once you've spent $2 billion to get it there, they're going to pay $60 million a year to keep it there as long as it works. And so, you know, the team is right in the end, but it's clear that they have a perception problem at minimum with the broader scientific community, who are the people who sit on these panels. And so they need to take a look at that in addition to coming up with more science objectives for the coming years.
Got some ice for that burn?
I mean, my mouth was literally hanging open. I was reading it because you just never hear this sort of thing in a publicly released document saying that, you know, this mission is not succeeding. It's basically the undertone that was coming out of the report.
They should have a high-level discussion and realign their priorities to a common basis, and perhaps have a new paradigm shift. The
spacecraft is in good shape, and so going forward, we can refocus and do science that we haven't had the chance to do in the last couple of years, and so we're getting our money's worth from this. But I think when you compare what Curiosity's done to what Opportunity has done, I think that it's a difficult comparison to make. and I think that may have been coloring some of the views of some of the panelists.
Yeah. Okay, well, we've got just about 10 minutes left because we started a little late, and I don't want to drag on too long. But let's just see if we can get some questions here. So Will-Eyed Oni asks, is that a blackboard on Brian's bedroom wall? Brian, do you have a blackboard on your wall?
I have a blackboard in my bedroom, and I have one in my office. Yes.
Do you have one in your shower?
I do not. But...
A dive slate is what I've heard recommended. You put a dive slate in your shower, and then if you're in there and the ideas come, which they always do, I mean, really, we should all just be taking more showers.
I'm a boy who likes my blackboard, so.
Yeah. So that's why I think it's the closest thing you can get to a blackboard in your shower. Jim Meeker says, my new address, my chair, Earth, Milky Way, local group, Virgo cluster, Laniakea supercluster, local filament, visible universe, metaverse. That's pretty great.
All right then.
Did you ever do that to be some snarky kid?
Yes.
And you were like, I know more astronomy than you do, and so I would write down my full address.
That was my AOL profile.
Yeah, we all did that.
Have fun fitting that on an envelope.
Yeah. Matthew Lemon asks, is the camera on Rosetta black and white?
All cameras on spacecraft missions are black and white. You can make color images by passing them through different filters and then combining them later in post-processing. And I'll make a brief plug for Matthew here. I'm pretty sure you can learn to do that in one of the Cosmo Academy classes. But often when they make...
We need Emily to come back and teach another class for us, though, because she was the one who was doing that. But she's finishing a book, so she has a good excuse. So we'll see if we can hunt up somebody else who she will not... They will not match Emily's excellence, but we can try.
Now, is that a microphone you're holding there, Matthew? Because it looks like a Tolkien pipe that you're about to, you know...
No, this is my low-tech solution to the fact that Google will not talk to my headset.
Right. Let's see, is there anything else? So Michael Jobin asks, who would have guessed that a comet would collect regolith? So is that what we're seeing, Morgan? Regolith on that comet?
Probably. So again, I'll make the comparison to the other comet, Sighting Spring. That one spent billions of years out in the Oort cloud, where there's basically nothing, and then millions of years traveling in to the inner solar system. Churi-Guri has spent millions, probably billions of years in the inside of our solar system, hanging out between Mars and Jupiter. There's a lot of dust out there, and over billions of years, you're just going to kind of collect dust on the outer edges. And until we land, it's difficult to tell a tiny, really thin layer of dust from, like shovelfuls of dirt. And that's what a lander does that a flyby or camera can never do for you. So when we land, we're going to be able to look down a little bit and see, is this more than, micrometers thick? And that'll tell us a lot about the history of the comet.
All right. Well, let's wrap things up. So before we go, though, I want to give everyone a chance to plug themselves and the things they're working on. So Brian Koberlein, where do we find out more? We've lost your information.
You've lost my information. You can find me on Twitter at Brian Koberlein, and you can find me online at briankoberlein.com. So if you know my name, you can find me.
And as I mentioned at the opening of the show, you have been pitching in on a few of the videos we've been doing for the Guide to Space. The award-winning Guide to Space. And in fact, right now, if you go to Universe Today, there's a video about what it would be like to fall into a black hole, and the core skeleton of that script is all Brian Koberlein. So. And then made way sillier by my co-creator Jason Harmer. So thanks, Brian. We really appreciate your help on those. Dr. Matthew Francis, where do we find out more?
You can find my main site is bowlerhatscience.org. My blog is galileospendulum.org. If you are interested in knowing more about what happens when you fall into a black hole, for example, or some more about this holographic principle that we spent some time talking about today, class begins Monday. Black Holes into Darkness which I am proud of the name of that class. No lens flare or Benedict Cumberbatch playing an Indian. But it will have lots on black holes. We'll ask and answer the question as far as current knowledge about what Stephen Hawking actually meant when he said black holes don't exist, and other fun stuff of that nature. So basically, it is taking the other side of black holes from the class I taught previously, which was focusing on the astrophysics. This is going to be talking about the fundamental physics of black holes.
And so again, where do people sign up for this?
cosmoacademy.org. Has our upcoming classes listed, including this one.
And if I haven't made this really clear, sign up for this. Like, come on. You could, like, literally spend weeks on end talking to Dr. Matthew Francis about black holes. Weeks on end.
Not even a big time commitment.
1 week and then another week. And you can spend time talking to Dr. Francis about black holes. So if you love this stuff and there's still slots available, there's like something wrong in the universe. So go and sign up right now. I'll wait. We'll just wait right here until everyone's signed up.
It's starting to sound like Jerry Lewis.
Yeah. All right. Operators are standing by. Yeah, and seriously, I mean, and definitely go and check out Cosmo Academy and take a look at all the courses we've got going on, because we are connecting you with the professors and the teachers and the people who know the stuff, and you can learn and you can follow on whatever topics really fascinate and interest you next. And so I will just keep on nagging. All right, Morgan, where do we find out more?
Yeah, well, first off, I'll be resurrecting our weekly Q&A over at the Google Plus Space community right after this. So if we didn't get a chance to answer your question, or you just want to pester me with difficult questions, I look forward to seeing you over there. You can find me on Twitter at Morgan Renberg, and you can read my ramblings at cosmicchatter.org.
What do you think about taking the conversation into the Weekly Space Hangout community?
I think that will reach a much smaller audience. I don't know. A lot of people see it on the Google Plus. Anyway, I think that might be an idea as well. So I don't know if we can somehow bridge that. I don't know if you can make it so we can connect both.
You would have to be in two communities at the same time. Anyway,
yeah.
All right, we'll crack this.
Out.
Yeah, we'll see what kind of response. So, but yeah, for today, definitely go to the Google Plus Space community, the one administrated by me and the team, and then we'll figure out where to go in the future. Okay, all right. Thanks, Morgan.
Yeah.
And Dr. Gallucci, or as Pamela calls you, Dr. Gugliucci.
She tries. It's cute.
She tries.
She calls me really, she calls me Noisy as if it's my first name, which I totally respond to. Yes, I am Dr. Nicole Gallucci with CosmoQuest, and also now with the Teen Science Cafe Network, and I'm teaching a class at Southern Illinois University, Edwardsville, so doing all the things this semester. Come to CosmoQuest.org, do citizen science with us, come read our blogs, interact with us on social media, and say hello, because I love your hellos, and I love to respond. And now that DragonCon is over, I can sit here and do things and work, so it's great. Yay.
Fantastic. All right, and so once again, publisher of Universe Today, by all means, go check that out. If you want to see stuff that I'm directly working on, check out our Parsec award-winning Guide to Space video series on YouTube. So we just released What's It Like to Fall into a Black Hole, and we actually got two every week. One coming out on Mondays and one comes out on Thursdays. So we've got mountains of them for you to watch. All right, so thanks everyone for joining us. Thanks for staying true to the spirit of the Weekly Space Hangout, even over the summer while we were all taking a bit of a vacation. We, as Cole says, we love you.
As some of you are taking vacation.
Some of us.
Someone's bitter.
Some of you were taking a vacation so you could work on other things harder.
It's
what really happened.
If the rest of you were anything like me, all we did was work on other projects as quickly as humanly possible to clear out some space. So, and thanks everyone watching. Really appreciate it, and it's great to see all of the fans, and the fact that you guys have set up a Google Plus community is just the coolest. So, all right, we will see you all. Astronomy Cast, we are going to be releasing the live show that we did at DragonCon, which is you'll love it. Is me asking the hardest questions I can possibly think of to a bunch of unknowing, unprepared space scientists and astronomers.
Really, we should all know you better than that by now. We should all be aware of this.
The topic given to me was the hard questions about space and astronomy, and what they thought that meant was like, how do we, people dealing in the space sciences, handle the tough questions like climate change and whatever. And the way I interpret it was, think of the worst murderous questions I could give anyone and just unleash them one after another and not accept I don't know as the answer. So that's what the first episode of Astronomy Cast will be, and I hope that comes out. We're hoping to get that out on Monday, and we're also going to do our next live show on Monday. So we're back to our normal time. VSP is coming back. I just don't really know where and how, but it's going to happen soon.
I think it's this Sunday.
Is it this Sunday?
I have not seen an official announcement, but that's what they said during the other Star Party one.
Huge props to Scott Lewis, who's been running the shows over the summer, and so we're going to get cracking again. I guess this Sunday. So
let's tentatively say Sunday.
All right.
Do it.
Tentatively say it. We're just volunteering Scott.
I will be dead because I teach at 8 a.m. Monday.
We'll see you all next week. How do I even stop the broadcast? I don't remember anymore. All right.
Forgotten everything.